Okay, now we're going to cover Kirchhoff's current law. Some people actually pronounce it Kirchhoff's, and I'm not sure which way is the proper way, but I hear Kirchhoff more common than Kirchhoff. So Kirchhoff's current law was one of two laws that he created. This was the first. And his law states that the algebraic sum of currents in a network of conductors meeting at a point or node is zero. Okay, that's a very fancy way of saying that if you pick a point in a circuit, any electrical circuit, the current coming into that point, the sum of those currents has to equal the sum of the currents going out of that point. So let's look at that a little bit closer here. I've just created a simple circuit here, and I have a battery and some resistors, and I have two connector points or nodes. In fact, I'll use the term node from now on in the rest of this lesson. So I have a node A and a node B in this circuit. And flowing into node A, I've referenced this current. And I have labeled that I sub 1, just so we can keep them apart. And then we have a current reference flowing in this resistor from A to B, referenced I sub 2. And we have another current flowing from A to B, but it's through this resistor, I sub 3. So let's solve for node 1, and let's apply Kirchhoff's current law. So we need to know all of our n's. So the current referenced coming into point A is I1, and that's the only one. And then the current referenced coming out of point A is I2 and I3. And those are all of the currents either going into or coming out of node A. So this is a much easier to understand way of stating Kirchhoff's current law than this long sentence. But the ins minus the outs has to equal 0. Okay? So my ins is just I1. And my outs, I have to add those two together, so I do that in parentheses here. And those are my outs. And I subtract those two, and that has to equal 0. Okay? So let's apply some numbers to this and see how this works. Okay, so for I2, I'm saying referenced in this direction, I have 1 amp. For I3, referenced in this direction, I have 2 amps. So I sub 1 minus the 1 plus 2 must equal 0. So I1 minus 3 must equal 0. Well, for that equation to work out, I1 would have to equal 3 amps. Okay, so that makes sense. We have 3 amps coming in to this branch, and we have 3 amps going out. Okay. All right, we have another node down here. Let's look at that. Okay, so we have node B. Let's solve for node B. We need to show another current on the graph here, and I'm referencing the current from B to the negative side of the battery in that direction. So my ins to node B are now I2 and I3, and my outs out of B is I4. Okay, there again, ins minus outs has to equal 0. That's Kirchhoff's current law. So I'm summing my currents, and I'm subtracting my I'm summing my ins and I'm subtracting my outs. And we'll apply the same numbers here. So we have 1 plus 2. Those are the two currents that are referenced coming in to node B. And we're going to solve for I4. So 3 minus the I4 is going to equal 0. And for this equation to work out, I4 would have to equal 3. Okay, so that makes sense. We have 1 plus 2 amps coming in. We're going to have 3 amps coming out. And also I4 here equals I1. Okay? Because we're talking about current, we're not talking about voltage drop, which will be Kirchhoff's next law. This current would have to actually equal that current. But this is a simple circuit. Let's look at a little bit more difficult circuit. But this is fairly straightforward so far, I hope. Okay, now here is a branch that we have 3 current references, and they're all pointing into the node A. Okay, let's see how this works out. Okay, for node A, I have 3 current references coming in, and I have none going out. Okay, so there again is Kirchhoff's current law, and so I'm going to add up all of my ins, and I'm going to subtract my outs, which I don't have any, so it's 0, and that must equal 0. So we'll apply some numbers here. We're going to say that I1 is 10 amps, and I3 is 5 amps. Okay, and we're going to solve for I2. So we have the 10 plus the I2 plus the 5 minus the 0, because we have 0 outs, must equal 0. So I2 plus 15, I just rearranged this. I added the 10 and the 5 to get to 15, and I rearranged it to where I2 plus 15 equals 0. For this to be correct, I2 can't be a positive number. It's got to be a negative number. In fact, it would be negative 15. Okay, so that tells you a little bit about this direction here. Okay, we're reading negative amperage. Okay, now I've been very careful to say that these are current references, these arrows. Okay, we're gonna look at that a little bit more when we solve for node B here. Okay, so for node B, we have no ins at all, and we have 2 outs. Okay, and I think you can start to formulate an issue right here, but this is the purpose for this current law, and we're going to find that out as we solve this problem. Ins minus our outs still has to equal 0. That is Kirchhoff's current law. We have 0 ins, and we subtract the sum of our outs, which are I2 and I4 in this case. We know that I2 is negative 15. We just solved for that when we did solving for A. So the 0 minus the negative 15 plus the I4 is going to equal 0. I4 minus 15 must equal 0, so therefore I4 has got to be 15 amps. So the reason why Kirchhoff came up with this law was some circuits, they can get to be so complex that you're not even certain which way the current is actually going to flow. So you can draw reference arrows like this on a schematic, and then you can use his current law to figure out actual current flows. So in this case, we have a negative 15 for this current reference. So that would be the same as me putting a ammeter on this section from B to A with my positive lead here and my negative lead there. And I'm going to read negative amperage, and The reason that is because the actual amperage, the conventional current or the whole current, is going to be flowing in this direction. And that's why when we reference it in this direction, it is negative. The actual current will be flowing in this direction. So a lot of people will actually state that the current is flowing this way, or the current is flowing this way, or the current is flowing that way. It's actually referenced that way when we apply Kirchhoff's current law. And if we have every reference correct, they'll all be positive. But in this case, this one was referenced in the opposite direction of the actual conventional current flow. So that's why it became negative. And that's the beauty of Kirchhoff's current law, is being able to apply his law to find out the actual current flows. So that is Kirchhoff's current law. This is part 1 of Kirchhoff's laws. We're going to have a part 2 where it will be Kirchhoff's voltage law. So we'll see you in that one.